I will talk about solving Python mysteries. I used to be a C++ developer for almost 19 years. We were building software for big banks and card processing centers. And then I had to debug all kinds of issues of this software running on kind of all these different kinds of proprietary Unixes like HPUX, AIX, and so on. And I had to do it over phone and email. So I had to learn some skills how to do it and learn some tools. Then the same, currently I work for Ebury, so it's a company also here in Spain. And yeah, still have to investigate some issues, and I still don't have access to production systems. And then I work on some other projects and some cybersecurity stuff. Yeah, so I like to solve issues and to solve incidents, and therefore kind of a bit selection bias. So just because I will talk about a lot of incidents, it doesn't mean that I'm a walking disaster. So it's not that everywhere I work it's full of problems, but if there's a problem, I'm the first online to try to solve it. And sometimes we get like HTTP 500 and it's okay, it is resolved automatically, but I have to know why it happened. So that's my personal stuff. For investigating systems, so the best advice I know of comes from people who do performance investigations. So this is Brendan Gregg, and he has written some books about performance tools, and he also is author of this observability tools map with different parts of operating system and which tools are available to investigate what's happening there. So I will touch some of those tools, but if you are interested in more of them, so just check this stuff out. I will start with the basic ones. And it's the process file system. So now we take it for granted, and when we learned Unix at university, everybody told that, well, Unix is this operating system where everything is a file. Well, it turns out that processes as a files were introduced only in 1984, so it's more than 10 years after the initial version of the Unix. But they were added, and now there's a lot of information inside this file system. So for incident investigation, there are a few of my favorites. So whenever I see some process that I want to investigate, first I want to understand from which folder is being run so that I know where to find the source code of the application and libraries. So this is typically under /pros/ the PID of the process and then / current working directory, so CVD or CWD. And this is a symbolic link to the actual folder, so you can use something like read link utility or ls-l to find the actual path. So this is like easy thing, and then you know if the application complains it doesn't find some templates or something else. This is the base folder where you start investigations. Another very important file is the environment of the running process. So typically applications get started through a bunch of shell scripts, and you never know which variables get overwritten or are added and removed. So this tells which are the actual environment variables with what the process is running. So the important thing here is that this file is kind of, it uses C-style string encoding. It means that every string is actually terminated by binary 0. Therefore, typically I use this translation utility to translate binary zeros into new lines, so I get this printout of nice like variable per line. And since most of our applications now are cloud-based, so this is typically the best practice to inject secrets into your application through environment variables. So when I investigate problems, I have options. Either I can ask for permission to retrieve some API keys to some external resources or database passwords, or I can look up this file and take it for myself without asking permission, and then be sorry later. Another very interesting folder under the process file system is the FD, so it's the file descriptor folder. So in Unix, file descriptors are numbers, and under this folder, those file descriptors are represented as links. So for each file descriptor, the numeric value you see to which actual file it's linked to. So there are some files which represent open sockets, some are linked to the terminal, some are linked to the open files. So how can I use this? So there's the Unix utility fuser, which is not typically installed by default, but basically it tells which applications are using a specific file or keeping it open. So you can just list files for all processes and then look for the interesting file, and you can find out which processes are currently using this file. So for me, it's, I know, so this is like Neo Vim opening some Lua log file. And this also comes handy when I have to restore deleted log files. So for purpose of presentation, I have written an application that writes logs every second. A single line every second. And then this log file has reached close to 10 gigabytes of disk space. And then so there are a couple of occasions where people say, oh, this is a huge log file, let's remove it, and then they are surprised that the disk space is not reclaimed, it's still being used. So what's the reason for that? Is that if you go back to the Unix, so Unix as operating system doesn't have like a concept of removing file. The system call there is called unlink, and unlink, what it does, it removes the file name from the directory. It doesn't actually delete the content of the file. The content of the file stays on a disk until the last process that has opened it closes it. So how can we use that fact? So one of that is restoring deleted log files. Let's say somebody deleted log file by accident, or the other case is, for me, typically what I see is that there's some log rotation that is not set up correctly, and there are new log files, but they are empty, and then the process is still writing to some file that is already deleted. So you can find out those files. So for my English environment of the Unix, it says that it's deleted by the end of the file. If you have Spanish set up, it probably says deleted in Spanish. Basically, you can see the file, and then you can use this file descriptor. In my case, it's 3. You can use it as instead of the file. So you can use tail to see what's being written to the log file, like in the real time, or you can use utility like cut to make a copy of everything that is there. So important note, so this is a symbolic link. So things like copying this symbolic link or moving this symbolic link won't work. So you have to use something like cat, which actually reads the whole content of this kind of file descriptor and stores it somewhere else. Yeah, so this was kind of the basic stuff. Then I'm often interested in like runtime behavior of the application, and developers typically use debuggers for that. Since I'm oftentimes debugging applications I do not know about, or I have to ask somebody else to run some commands on behalf of me. So I typically use strace. So strace tells which kind of system calls the application is doing. So the best thing is kind of language agnostic. I do not care if this is a Python application, if it's a Golang application, if it's a Java application, I can use strace on it. And the best feature is that it doesn't require root access. So there are other tools which like perf and bpf trace which do require root access, but if I tell admin, please run strace for me, you don't have to become root to run it, admin will be more likely to help me out with this. However, but on the opposite side, if I tell him like, run this under the root, then it goes through the security review and it might be stuck for days. And another feature I like in the age of like cloud applications is that you can also install the same package without root access. So it's just downloading those two packages from whatever your distro is. You unpack them and then you set up the library path. So basically you need a single library and then you have the binary and it runs. And I have installed it inside Kubernetes pods to see what the application is doing on Kubernetes. So it's like pretty convenient. Now, how do I use it? So the basic usage command is that you can either attach it to the application that is already running by specifying the process ID, or you can run like existing Linux command under it. The most important flags are -f, so it tells if the application spawns new threads or starts new processes, please follow those new processes. Then it's -TTT, so it prints the very detailed millisecond timing information, and then I typically forward output to some file for later analysis. And then it's this -s and some bigger size. So by default, strace cuts the output so it fits the screen. Oftentimes it's like really, really short, like 20 characters. So I ask it to print like 1 kilobyte so that I have better idea of what's happening. There are some other flags, but let's skip those. So now the output. So this is actually output of one of the running applications. And even without knowing much, you can see that it has this system called send to, and it sends something that contains select distinct on loan underscore something. So it's kind of, you get the idea that it's trying to execute a query, and then it has receive from, so it receives something. So this is like a short output, but you can see that there's the request ID. So it's receiving some fields in response. The output of this utility actually comes in two parts. So first, for each system call, it prints the entering part. So it prints the parameters that are passed into the system call. In this case, it's providing the file descriptor and then events, and then some other one and -1 as the inputs to the system call. And then once the system call returns, then the strace prints the result of the system call. In this case, the result is equal to 1. And and strace typically prints out some support information for you to like better understand what actually happened. So that's the FD12 and so on, then R events pollen. And the same for, let's say, for this receive from. So it starts receiving from file descriptor 12, and once it receives the data, it prints the data and it prints the length of the data that was received. So, and why this is useful? Because it allows to distinguish between blocking and non-blocking system calls. The idea is that like with the least effort, what you have in operating systems are the blocking system calls. It means that you ask the kernel to do something and it's fine to block indefinitely inside the kernel, and your application will not get the control back and it might get stuck there forever. And obviously that's like not very nice for interactive application. And oftentimes this blocking behavior is discovered on like some errors or problems when you encounter them. Then the non-blocking approach, it requires a bit more work. So you have to either set the file descriptor in like non-blocking mode or pass some additional no-wait flags. And in those cases, the kernel will return with a specific like error code saying that, oh, please try again later. So there's no data for you right now. And then application can decide how to handle that. If you haven't done a lot of systems programming, so those are the main calls you expect to see. So if I see that application is kind of blocking on something like ePol select, pselect pol, and there are other variations of this, This is fine. This is actually what I expect to see from application. It's waiting on some multiple sockets, on files to be opened, and so on. Then just for the completeness, writing and sending data, typically it's like happening instantaneously. There are very rare issues. Typically something is really, really wrong with the disk device when you see those system calls get blocked. Then the accept system call, which accepts the incoming connections. Most of the time, most applications implement this in a non-blocking way. However, if it's in a blocking way, it's kind of okay, because if you have problems, you discover them quickly. The next one is more interesting because connects to the outside server, to specific IP and port. And if you see connect being stuck, it means that the timeout has not been implemented. And this is like a really, really serious issue. So we had application which actually had timeouts implemented. And the application kind of timed out, and then it tried to report problems to Sentry. And turns out that the Sentry wasn't implementing the connect timeout, and Sentry got stuck forever. And yeah, so eventually we had to kill application because of this Sentry bug. So this is now fixed. It was fixed like 6 months ago. And a similar way, read and receive from, if you see those stuck, it's really bad. It means timeout has not been implemented. And in higher level languages like Python, it's simply just passing like timeout parameter to most calls. Wait for, it's typically waiting for another process termination. And mutex, so this stands for fast user space mutex. So this means that the application is waiting on a lock. And this is like typically a symptom of a deadlock within application. So I have a sample deadlocked application here. And this also shows another important feature of the strace. Whenever you attach to the process, it will first tell how many threads there are in the application. In this case, there are 3 threads. And then it will proceed with printing state of each of the threads. So first it prints thread that ends with 07, and it says that it's waiting on futex with some futex address, let's say address A. Then the next thread, 06, is stuck on the futex that is on a different address. So let's say address B. And then it prints that the third thread is sleeping, then it's retrieving process ID, then it's writing something and so on. But those previous 2 are stuck. And so because they are stuck on a different, waiting on a different mutex, so it's a deadlock. So each of the threads is holding one lock and waiting on another. So this is, I've seen like cases like this a couple times in production. So pay attention what is printed when you attach with strace. And now story time. So we had a Django application that was kind of working slowly. It had background tasks that didn't catch up and didn't produce results soon enough to the user. So we connected to the server. What was interesting that the CPU was kind of under a high load, but that was typical for the application. However, the I/O load, so writing data to disks, was also, so the disks were also loaded. So the tools I used, the tool I prefer to use is called Nmon. So this is like an old school tool, but you can get the same numbers from IOStat, like standard utility, if you pass it -x. So it will print not only the like actual numbers of megabytes per second, it will also print like utilization percentage of the device. And that's the number I'm typically looking at. So I don't care how CPU operations can CPU do. I'm interested, is it loaded 60%, 80%, 70%? So that's the same for IO load. So we found out the process IDs of some background tasks attached to them. And what they were doing this stat system call, which retrieves the file size of the file, and typically also it's used to check if the file exists. And the files were like some JSON files in this specific /storage folder. So what's the story there is that this application had a specific custom file field, like, so that's a Django thing, and it had additional property where it looked for the file either in the backup folder or in like active folder, and then they had like a cold backup folder. So it was checking for a file in which folder it exists. And by some accidental change, the background task was loading more objects than needed. So, and at this stage, probably what most of us would do is, okay, so we need to fix the bug. So we want to introduce a new some caching mechanism and so on, but that was not the case. Because why? Because this I/O utilization was quite low, but it was also doing a low number of megabytes per second. And long story short, there are two numbers. What vendors give you is the throughput, but throughput can consist of two like parameters. It's either operations per second or the block size, and you can get good results by increasing operations per second or increasing the block size. So typically vendors increase the I/O size and get good numbers like that, but individual operations are really slow. So long story short, we checked the servers and we had a brand new server with brand new storage device, and it was doing something like 27.8 megabytes per second on this specific block size. So the block size is for the databases typically work with 8K and file systems with 4K. And it was roughly 12 times slower than our old Hetzner machine. So we pushed the server provider to fix the performance. They eventually managed to double the speed, but it was still lagging behind what is normally expected from the hardware. So we didn't fix the application, we pushed to fix the hardware. Then don't have that much time. So networks. And I work in fintech, so oftentimes when we connect to some partners, we have to set up firewalls, open firewalls on both sides, and then so networking teams on both sides say, yes, our job is done. Now test your application. We start testing application, nothing works, and then they say, oh, it's a problem with your application. And for developers, so we don't have that many tools. If you Google, it will tell you to use ping or traceroute. However, if you have good admins, then they have disabled ICMP and UDP traffic, as they, I guess, should. But those tools are useless without this traffic. So what to do instead, there's a tool called TCP traceroute, which uses TCP packets, and you can simulate the traceroute tool. So this is kind of the output you get. So it prints the whole path, how the packets travel through the network. And then you show this to your network guys, and they say, oh, well, I wonder why the connection went out through this path, not this path, so therefore it gets a different IP address and so on. So, and then they understand this output and they can fix problems on their side. And let's go into story. So this was when we were trying to develop new application using Kafka. And so it was, we had a consumer, is consuming Kafka events, enriching those and producing new events as a result. And it all worked at around 20 events per second, which is, I mean, too low, if you ask me. So we went to investigate. So first thing, you turn on the, so we used the librd Kafka. So it comes from Confluent. So it really, in the printouts, it said that it's using 43 milliseconds to send a single message. Okay, it's a lot, but let's dig deeper. So we tried TCP traceroute. So to test the network latency between the application running inside Kubernetes to the Kafka cluster, and it was like a single millisecond. So the network is not to be blamed. Then we used strace, and strace showed that actually application was stuck in the poll, networking call. And at this point, it's something that you just have to know. And so there are kind of numbers you have to know. So if your single call is taking around 40 milliseconds, or you get only around 25 transactions per second, then most of the time is this TCP no delay. And people say that it's Nagel's algorithm, but In reality, it's like interaction between Nagel's algorithm and the delayed ACK. And people solve this issue by setting this TCP no delay, which disables Nagel's algorithm, but I think that the delayed ACK is the worst one. So Nagel's algorithm is kind of okay. So what we did, so there's the non-default setting in the Kafka client to disable this Nagel's algorithm, and then the performance got like 10 times better. Kafka still hasn't fixed that by default, so it's 2 years already. I also found where those 40 milliseconds come in the Linux kernel source. So there's a really delay of 40 milliseconds, hard-coded. Another story time about timeouts. So on this time, we had a Python application that was doing calculations. So you send the CSV input, and depending on number of rows, it was taking some time to produce results. And we had a Scala HTTP client running in Kubernetes. And of course, everything worked on developer's environment, on the local machine. And sometimes the HTTP request took minutes to complete. So not the best solution to use HTTP, but it is what it is. And when running Kubernetes, the small requests were taking a couple of minutes, which is kind of okay. And larger requests took 2 hours before timing out. And what's interesting, the larger request still worked when it was sent through using curl. And so this is like my, motto or something like that. Whenever you have networking issues, ask what would curl do. And so I checked what is curl doing using strace. So number one, it's really setting this TCP no delay that Kafka is not setting. And then it sets those three parameters called socket keep alive, TCP keep idle, and keep interval. And why does it so? Because curl knows best that the Linux defaults really suck. So what Linux defaults say is that it will send the first TCP keep alive packet only after 2 hours of idle time, and then it will do it 9 times with 75-second interval between them, so it's really bad. And if you say, well, this is Scala, and how does it relate to Python? So Python is actually not better, so it doesn't set those keep alive flags. However, it does set TCP no delay, which means Python is better than Kafka, at least. And what's happening? It turns out somewhere in between there was a firewall or gateway that drops connections after 5-minute inactivity. So client is not aware that the connection was terminated, server was not aware, and so client, after waiting for 2 hours, starts sending those keep alives, and then after a few more minutes, it kind of times out. And again, so this is like a bad case. You shouldn't use HTTP for that. However, all of us, we have long-lived TCP connections, and those are database connections. And luckily, the Postgres supports this keep alive, idle, and interval parameters, where you can override the Linux default values and have a better result. So you can have your database connection stable. How I solved that for Scala, there's actually a library that intercepts socket creation, and it sets you can kind of, and it will force all sockets to have this 40-second idle time and interval. And and this is, if I'm too lazy to look up the configuration parameters or how to pass them down to the lower level to actually get those set, I just load this library and it takes care for me. And so it works fine until you have Kubernetes and like service mesh. And we have this layer 4 proxy, which is Linkerd proxy. So it intercepts TCP connections and then makes TCP connections on their own. So between application and Linkerd proxy, we have perfect keep alive, but then Linkerd doesn't set those by default again. So it loses connections to the database. So just be aware of things like that. So we ended up killing Linkerd proxy at all. And that's it. I'm also out of time. So the summary is that Learn the process file system. You will find a lot of stuff there. strace is my favorite tool to inspect any application. Same for TCP traceroute. So this is the tool that helps you debug networkings in this age. Then set timeouts for all networking calls. Keep in mind this 40 millisecond and 25 transactions per second. It's just the magic number. You have to know that it's Nagel's algorithm. Then set up TCP keep alives. And also, I mean, it's the like overall message, like know the root cause of each problems. So before jumping, introducing caches and trying to solve problems in application, actually measure what the system is doing. And so my pet peeve is this disk IO, because now with the cloud providers, they say that their disks are good, but most of the time they are not. So just try it yourself before doing some drastic changes to your application. And that's it. And we have some time for questions.
Any question?
Yes, thank you for presentation. My question, have you tried a tool that's called PySpy that allows you to make sampling what Python does and can also draw you flame graph which for example, function or which Python opcode takes more time than others?
So the tool was?
PySpy.
Yeah. So locally, for myself, yes. So the problem is I typically have access to some systems, so I focus. So this tool works in all conditions for all applications, so I go with that. So once I find out that the system calls are not the issue, or it's just burning CPU, okay, now I take it to profiler and then investigate further.
Okay, thank you.
Any other question?
No. No. Okay. Oh.
It's pretty simple. What's the reason that you don't have access to
Production?
Yeah, is it just client security?
So I work in finance, and for example, for cards, it's the number one, it's the bank's network. So typically banks have like external network and internal network, and me, even as a coming from vendor company, I don't have access to that. I have to like write admins, please execute this command and send me the output. And if I tell them, oh, start debugger attached to this process, type these prints and something like it, it's not going to work. If I tell, oh, there's this tool strace, it doesn't require root access, just run it for a minute, send me the output, I will analyze on my side. So it goes through every time.
Thank you.
Any questions?